Okay, so hopefully the sound is okay on this. This is a test run, but if you happen to be checking out things before the class starts, I wanted to go through the first lecture, at least portions of the first lecture prior to the start of class. So hopefully you can both benefit from this. If this works out well, my goal is to record lectures this way, break them into different sections. And I apologize because I got a behind the scenes error already. So I'm back. So my goal is to turn these lectures into sectional pieces. So whereas during lecture, the ones that are recorded in the Zoom channel will include, let's say, Monday. So for instance, Monday, we might get to this much, and then Wednesday, we might get to there, and then pick up there on Thursday, etc. That's going to be one plan. But if all goes well, I want to set up a lecture system where I'll have a certain amount on this topic, and then another thing on formal charges. That way, when it comes time to review, you can look it up by date. That'll be in the Zoom Pro. But then on the YouTube version of this that I want to generate, it'll be by topic. So that way, if you want to just review a specific topic, you don't want to go through a whole lecture. So bear with me. This is a project that is going to be a learning curve as we go. And as I mentioned in an email I sent out to everybody, any insights you have, very much appreciated. We'll go ahead and get started. Hopefully the sound is good on this. So I want to start with what's known as the HONC rule. And so one of the things you're going to need in this course is, got to remember some of your tail end general chemistry, in particular structure, bonding, some of those things that you picked up. So we'll go over sigma bonds, we'll go over pi bonds, we'll go over Vesper theory in terms of angles. The good news is in OChem, carbon only makes up to 4 bonds, so you really can draw a limit at 4 electron pairs around the central atom, but it's still, you have to go back through it. So some of the things that will pop up, bond angles, number of bonds, types of bonds, and so forth. But before we do any of that, skill you're going to desperately need in this class is the ability to count to 4. It's going to be important because carbon makes up to 4 bonds. So no pride whatsoever. Seriously sit there and count 1, 2, 3, 4. If you can do that successfully, you're going to do just fine in the early part of this class. That is because the atoms we care about, the atoms that make up the majority of organic chemistry compounds, although we call it carbon-based chemistry, you're going to find a lot of nitrogen, oxygen, and hydrogen in these compounds, as well as some other elements as we get further into our study of it. But you'll find hydrogen makes 1 bond, carbon makes 2, or excuse me, oxygen makes 2, nitrogen makes 3, and carbon makes 4. So these lines represent the bond portion heading to the hydrogen. There's has to be some atom here. Oxygen makes 2 bonds. It's going to be to an atom here, an atom here. Nitrogen makes 3 bonds to a nitrogen bond to nitrogen on this side, and here. And finally, carbon makes 4. These don't represent any 3-dimensional accuracy. These are just simply lines, and eventually this is going to become part of what we'll call a Lewis structure. But for now, as long as you know that rule, you'll be in good shape. So consider the molecule H2O. Something we study, we know, it's like we use the term so loosely that it's almost an automatic in our mind. So I'm going to draw a potential structure, and I want you to apply the HONC rule. Does hydrogen make 1 bond? So in this case, hydrogen here is part of 1 bond. Looks good. This hydrogen in the middle is part of 2 bonds, which means I've messed this up. Oxygen, only part of 1 bond, mess that one up. So that can't be your connectivity. Your connectivity is such that hydrogens can only make up to 1 bond, oxygen's going to make 2. We'll learn some exceptions when things are neutral, but for now, hopefully this is okay. So let me go ahead and erase my mistake and see how this works. So you can't have an HHO, but if we switch positions, let's see if that still works. Hydrogen, 1 bond, check. Oxygen involved in 2 bonds, check. Hydrogen involved in 1 bond, check. It works, perfect. So the HONC rule has been satisfied. H makes 1 bond, O is making 2. So make a little more complex molecule here. Carbon, nitrogen, and hydrogen. One of the things that you're going to have to develop early on is a sense about where atoms will be. So if you only make 1 bond, you can't really be in the center of anything. You have to be on the periphery. So I generally put hydrogens in last. They're going to be on the outside perimeter. Carbon and nitrogen, on the other hand, make a significant number of bonds, 3 and 4 respectively. They're going to have to be in the middle. The other thing we're going to have to take into account, there are only 5 hydrogens making 1 bond each, whereas nitrogen and carbon combined will make 7. So you can't have just hydrogens bonded to nitrogen and just hydrogens bonded to the carbon. There's got to be at least 1 carbon nitrogen bond. So I'm going to toss a structure out there. You'll notice I have nitrogen and carbons in the middle, and then 5 hydrogens. So let's double check our HONC rule. All the hydrogens meet the stipulation of 1 bond. We're good. Looking good so far. Nitrogen makes 1, 2, 3, 4. So I messed that one up. Carbon makes 1, 2, 3. Mess that one up. So I need to get rid of the carbon and nitrogen. So a couple ways I can do it. I can redraw the whole dang thing, or I'm just going to switch the carbon and nitrogen. So let's see what happens. Now, do we have it right? Carbon makes 1, 2, 3, 4 bonds. Check. Nitrogen makes 1, 2, 3 bonds. Check. So our structure. So again, I'm going to go ahead and erase what's here and say we have to experiment. Is it okay to make mistakes early on? You bet. So if I put the nitrogen and carbon in the wrong spot and I figure it out, I just simply fix it. Early on, your job is to figure out the way things work, and making mistakes like that is actually really valuable if you correct it. So first, early on the first day, I'm going to mention something called developing your wrong-term memory. So wrong-term memory is where you take something you did wrong and you develop it. You don't try to remember it's the wrong thing. Instead, you figure out what you did wrong and the algorithm that it takes to turn it from the wrong answer to the right answer, how to get the right logic there. It's actually a really powerful way to learn it. It's an active form of learning. I'm going to push it like crazy. So I know this is the first time some of you may be seeing my style of lecture. My style will be to make lots and lots of mistakes like I did here with water and like I did with aminomethane. I made mistakes and we corrected them. Okay, terms you're going to know. OChem, mentioned again early on, it's a big vocab push in the early part. There's going to be so many words that don't know. Break it down. Mono, 1 valent, 1 connection in the valent shell. So hydrogen has 1 valence electron, it makes 1 bond. Oxygen makes 2 bonds using its valent shell, so we call it divalent. Nitrogen makes 3 trivalent, and carbon makes 4 tetravalent. So it's important to know mono 1, di 2, tri 3, tetra 4, and so forth, and valent connections to the valent shell, outermost shell. Okay, so I'm feeling pretty good. So now it's time to apply it. Again, mentioned early on, OChem comes to you when you do lots and lots of practice, but not just cursory practice of writing out right answers, but truly thinking through a question and spending all the time it takes to develop really good habits. So in this case, H's, we know H's make 1 bond, carbon makes 4, oxygen makes 2. So there's a little bit of a system we go through with this. So what I want you to do is try to figure out which ones do you want to put in the very middle. Okay. So carbon makes 4 bonds. That's a candidate for the middle. Hydrogen make 1. They're definitely a candidate for the periphery. They're not going to be in the middle. O can kind of be in the middle, I think, because it has to make 2 bonds. So it's got to be a connecting atom in that sense. So start with interior central atom. I'm going to pick carbon because it makes the most bonds. Makes 1, 2, 3, 4 bonds. O makes 2 bonds. So I'm going to put an O probably there. And honestly, it doesn't matter where I put it. Totally up to you where you put it, but I'm going to put that one in. O makes 2. So we make 1 to carbon, 1 to whatever it's going to be for now. I don't know. Then I have 4 H's to fill in. The structure is written as kind of giving me a hint that 3 of the H's, H3C, will be located on carbon. 1 of the H's will be located on O. So an H and H and H and an H. So 4 altogether. So it's not so bad, and you get used to it. And I'm going on the assumption that many of you have done this when you took general chemistry. That isn't completely new information to you. But if it is, go back and do things slowly. Be really, really methodical early on, because the more you build a solid foundation, the more you can stack information on top of it. Leave any holes in your foundation, in your structure, it'll collapse. Okay, so I'm going to take advantage of two things now. I'm going to follow the same set of rules, start with interior. Carbon makes 4, so I know that those are interiors. O makes 2, so it's pseudo-interior. So I'm going to go ahead and put it in the middle, and the H's are on the outside. But take advantage of the way they've drawn it. 3 H's on carbon, just like we saw here. So it probably has the same thing, a carbon with 3 H's connected to, in this case, an O. So notice this part here matches this part here. The difference is, instead of an H here, apparently has another C with 2 H's and a carbon with 3 H's. So let's start with our carbons. I have a carbon, check, and carbon check. I put these two together because they're coming at the end. I put this one by itself over here. I'm going to put an O in the middle because, again, O is going to be pseudo-interior. It's going to be on the inside, but it only makes 2 bonds. I'm going to go through the same rules I did before. So start with interior, which we did. Draw all of its bonds. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Perfect. Second atom we're going to do, non-hydrogen atom, in this case, is oxygen. So I'm going to put my O right there because I know it's got to connect to 2. And I have spots for 1, 2, 3, 4, 5, 6, 7, 8, 3, 5, 8. So perfect. Set. I have the molecule built in. Okay, so let's try one more. This time I'm going to try to do it in writing. So same set of rules. Start with interior central atom, which in this case is carbon, but this is kind of weird. I have a CH3, just like I have here and here, but apparently I have 2 of them. So I'm going to have to put 2 carbons there. So I'm going to draw it like this. And it doesn't matter how you draw it, but I'm going to put 2. Then I have another carbon here. So I'm going to put another one there. So I've done start with central atoms. Going to draw in all of its bonds. So 1, 2, 3, 4. Making sure I have room for 1, 2, 3 H's. And then same thing here. 1, 2, 3 H's in this. And then the central atom has an H apparently. So I have room for an H. And then I have to figure out what's going to happen with sulfur. So sulfur is a little bit of a tricky one because it has an expanded octet, but in the absence of oxygen, we're going to learn that it's going to end up being a thiol in this case, or just sulfur will make 2 bonds unless it's highly oxidized, an organic compound. So I'm going to put a sulfur as one of those atoms. So I draw in all the bonds. I now want to put in, sorry, I'm being kind of tricky here. I want to put in non-hydrogen atoms. There's my sulfur. And then last but fill in hydrogens. There's H3C, one of them, H3C, another one, and an H here for this. So let me just double check. 3 H's on a carbon, check. 3 H's on the other carbon for the 2, check. H here. I apologize for my messy writing. This is partly the program. Keynote, the writing, the pencil connection is poor. And then plus, not that you would know this, but there's a big old stencil right about here. So I'm going to have sometimes just have them be kind of ugly or not connected. You're going to have to pretty your notes up, make them prettier than what I'm doing. But drawing the connections, pretty straightforward, as long as you follow the HONC rule. H makes 1, O makes 2, N makes 3, carbon makes 4. Sulfur being right below O in the periodic table be similar, it will make 2. Phosphorus being below nitrogen will make 3. Use your judgment like that. So why exactly is the HONC rule what it is? 1, 2, 3, 4. This takes a little more understanding of atoms. So again, I'm going to go back to GChem. Hydrogen is 1s1 if you remember. So I'll go ahead and put that there for hydrogen, 1s1 as a single atom. So as it stands, it only has 1 electron, so it can only share 1, which means it can only make 1 bond. The rest of them are a little bit different. Oxygen, if you recall, 1s2, 2s2, 2p4. It ends up, we don't care about the core shell. It's not going to be involved in bonding, but it involves 2, 3, 4, 5, 6 valence electrons. It's going to draw 1, 2, 3, 4, 5, 6. You can only be up to a pair, so one lone pair there, another lone pair there. These two are radicals. So because it has these two unpaired electrons, it can make two bonds. So hydrogen, 1 electron, 1. Oxygen, 2. Nitrogen, let's go ahead and put the electron configuration, 1s2, 2s2, 2p3. Again, core shell I don't care about. So it has 2 plus 3 or 5 valence electrons. So we have 1, 2 in a pair, 3, 4, 5. So it can make 1, 2, 3 bonds because it has 3 unpaired valence electrons. Finally, carbon is going to be 1s2, 2s2, 2p2. Don't care about core. There's 4 electrons total. So we can go in singly before they pair up. So 1, 2, 3, 4. We're all done. Make 1, 2, 3, 4. So it's a number of bonds it needs to complete its so-called octet. So this is going to be called the octet rule. Obviously, hydrogen is just one single electron, so it only makes one bond. So it's not going to fit an octet rule, but it's its own little entity. But for carbon, nitrogen, oxygen, they're set. Okay. So onward we march. So the octet rule is mentioned, complete valence shell. A few things is atoms in lower columns, such as I mentioned, sulfur and phosphorus, probably should have had silicon in that list, the ones right below carbon, nitrogen, oxygen. They want to obey the octet rule, but they have the ability to expand their octet. Silicon can't do much, but in theory, phosphorus could potentially go up to 10 electrons in its coordinated shell, so it can make 5 bonds. And then sulfur could go up to as many as 6 bonds. You've seen this. So, looking good so far. This is going to happen a few times. The coloring at the bottom, this is my own color coordination that reminds me of when I made these slides and when, like, how recent, how old, and how I fuse them together. So this is my own color coordinating system. Nothing's changed. It's still the same lecture. But I'm a big proponent of loving the big picture. So the big picture in this case is going to be the number of bonds it can make. So carbon, we mentioned, can make 4 bonds total because of 1, 2, 3, 4. But it's going to be a little bit tricky how it does it. So carbon can make 1, 2, 3, 4 in what we're going to call a tetrahedral arrangement. And that's 4 single bonds, 4 sigma bonds, as it's called. But as you learned before, and we'll review here, you can also make 3 sigma bonds and then 1 pi bond. So it's going to be sigma, 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 but pi. Or it can be sigma, sigma, pi, pi. So knowing these options is important. So all 4 bonds could be to 4 separate atoms. You have 3 atoms where you get a double bond to one of them. Or you can get 2 sigmas, 2 pi's. So it could be a triple bond. You could, and this is really rare, carbon dioxide being in a few cases can happen, but you can also have that arrangement for carbon and still bond 2 atoms, sigma and pi, sigma and pi. Nitrogen, only 3 bonds, all 3 single, or it would be 2 atoms with a double and a single, or it can be 1 atom with a triple. So that's pretty straightforward. Oxygen makes 2 bonds, so 2 single bonds or a double bond. And hydrogen is our fortunate, simple, and easy one. So this is the HONC rule. So I will pick up in the next thing I record what our next topic will be. But I'm hopeful that this makes some semblance of sense, that this is actually kind of easy for you. So I apologize for the very unsmooth way I'm going to exit out of this, but I'm recording this in such a way where I can't access Zoom unless I make the screen go in kind of an ugly situation. So I apologize if you can read everything there, but I'm going to stop the recording and hopefully talk to you soon. Thank you. Bye.